This video is about vector fields. We're going to start the video by looking at an overview of multivariable calculus. So we'll think about where we've come from and sort of where we're going as we finish up the calculus sequence. Then we'll talk about this chapter, which is all about vector analysis. And we'll discuss the major tasks of the chapter, what we're trying to do. And then we'll start by discussing what a vector field is. We'll define it, and I'll show you some examples. We will discuss the del operator. You've seen it before. It looks like this. I'll define that for you. And then we will look at the divergence of a vector field F, and I'll provide an intuitive interpretation of what the divergence means. And we'll discuss the curl of F. I'll show you how to calculate it, and then we'll provide an intuitive interpretation of that as well. So let's think about where we've come from. In pre-calculus, Calculus 1, Calculus 2, you were still dealing with functions of a single variable. All we had at that point was y equals f of x, and f was a function, and it took a real number x, and it mapped it to a point y, which was given by f of x. So in general, f was a map. It was taking a number from the domain of f, which is a subset of the real line, and it was mapping it to another number in the real line. So of course, we're familiar with lots of single variable functions. Here's my sort of classic example, y equals x squared. Every x is associated with one y. A real number over here maps to a real number over here. And then we have the graph of the function. Now, when we started Calculus 3, we said instead of mapping from a subset of the real line to the real line, or from a real number to a real number, now we want to extend this to n dimensions. And we started that process with vector valued functions. So we said, let's take a real number t, and instead of mapping it to another real number, let's map it to an ordered n tuple. And most of the time, that ordered n tuple only had two components. Sometimes it had three, but in general, R took a real number t, and it mapped it to this point. This actually yields a vector, but we really didn't focus on the vector. We focused on the terminal point of that vector if it started at the origin. And we said this R function, it takes a real number t, and it maps it to this n tuple in n-dimensional space. Or in general, R would take a number from its domain, which was a subset of the reals, and it would map it to n dimensions. So I might take, if n equals 2, I might take a real number and map it to a point in 2D. Or if n equals 3, I might take a real number and map it to a point in 3 dimensions. But all of the math that we studied generalizes to n dimensions. Well, almost all of it. Let's see. So let's say we've got r of t, and r of t is a vector valued function in 3-dimensional space. So maybe there's a curve given by r of t. So this is a space curve, C, given by r of t with components x of t, y of t, and z of t. And as t increases, we trace out the curve. Now r of t is a vector. It's the UR here vector. It starts at the origin and goes out to a point given by x of t, y of t, z of t. So it tells you your location at a particular value of the parameter t, and it says at that value of t, you are here. And at a different value of t, you're over here. And at a different value of t, you're over here. So it's sort of a pointer. It points right there at that location. Even though this is mapping from a real number to a vector, we're not thinking of it that way. We're just looking at the terminal point of the vector. So we're thinking of this as mapping from a real number to a point in n-dimensional space. So we said, okay, we started by mapping a real number to a real number. Then we said, let's take a real number and map it to a point in n-dimensional space. And then we said, let's do that the other way around with functions of several variables. Or you can say multivariable functions. Now for the most part, we stuck with functions of two variables. So we'd have z equals a function of x and y. So every x, y in the domain down here so maybe this is x, y, and z equals 0, maps to a point. And as x and y take on different values in the domain, they map to different z values. When we put those all together, we get a surface given by x, y, or whose graph consists of the points x, y, and z equals f of x, y. But again, the principle is the same as what we studied previously. Only now I'm taking, well, let's not focus on this function of two variables mapping to a single variable. Let's go back to n dimensions. Let's say I've got a function of x sub 1 through x sub n, and that gives me w. Well, in general, that's going to take this ordered n tuple, x sub 1 through x sub n, and it's going to map it to a real number w. So we're going to take an element of the domain of F, which is an n-dimensional space, and we're going to map it to a single real number. At least in this class, in this chapter, we were looking at real valued functions of a single variable, or real valued functions of several real variables. Now, if n is 2, we get a surface. If n is 3 or more, we don't get surfaces. We get what are called hypersurfaces. But we can still do a lot of the math that we talked about in the chapter over functions of several variables. A lot of what we did in that chapter generalizes. There's just a couple of things that aren't as easy when you're working with functions of n variables as opposed to functions of two variables. But we went from R into R, then we went from R into Rn, and now we've gone from Rn into R. And then the next chapter in our multivariable calculus class was all about multiple integration. So rather than finding the area under the curve given by y equals f of x for x between a and b, using an integral that looks like this, this is what we did in Calc 1 and Calc 2. It's really more Calc 1, but we continued to use the idea in Calculus 2. we said that represents that area under the curve. Or if the function is sometimes negative, we called it net area, area above the x-axis, minus the area below the x-axis, and also bounded by the curve y equals f of x. And then we said, okay, let's think about this differently. Rather than finding area under a curve, let's find volume under a surface. And so we had z equals f of xy here. And maybe we had some region in the xy plane down here. And we wanted the volume under this surface above the region R. Well, then we said, well, just take the double integral of the z values. So I've got the z values, which would provide a height of a little rectangular prism, and then multiply by dA. When that dA is finite, it's delta A. We've got delta x times delta y. And delta x times delta y times z is giving me the height of this little rectangular prism, And so I do that for all of the little rectangular prisms in the region R, and then I add them together and I get this volume under the surface, or net volume under the surface. And we talked about how to evaluate this. And then we also said, if we want volume, well, there's something else we can do. Maybe if we're going from one surface to another surface, so z equals f of xy is up here, and z equals g of xy, it's a bad looking surface, is down here. Rather than looking at the volume between two surfaces, we could do that. So we'd have the top function minus the bottom function. And I make my little rectangular prism, it'll look like this. So that's that height of my rectangular prism times a little delta x times little delta y there in the xy plane. Got that right there. And then we add all of those up. We said, instead of doing that, what if we did this? What if we did the double integral over R and we let z go from the bottom function to the top function? And then we said, maybe we'll call that region in between F and G the solid region Q. I could find the volume of Q using a triple integral rather than this double integral. And then we extended the idea for different integrands, integrands other than one, and we said if the integrand was the density, we could find the mass, and all of that. So that was where we were. So we started with mapping from R into R. Then we mapped from R into Rn, and we got these curves. And then we mapped from Rn into R. And if we were mapping from R2 into R, we got surfaces. And then we looked at multiple integration. Instead of just integration with respect to a single variable, now we had double integrals, and we had triple integrals, and they all represented something. Now this next chapter is about vector analysis. In this vector analysis chapter, we're introducing a new type of function. So Calc 1, Calc 2, and everything before that, you had a function of a single variable. So we went from R into R. Then we had R of t, which mapped from a real number t to a point over here. And actually, these should be defined on their domains, which are subsets of these real numbers, but I'm getting a little informal with my notation. And then this one, this F, mapped from R2 into R, or in general, we would map from Rn into R. You see the one thing that's missing? Got R into R, we had R into Rn, and then we have Rn into R. The last possibility defines what's called a vector field. And a vector field, F, assigns an n-dimensional vector to every point in its domain, and its domain is a subset of n-dimensional space. So basically, we're going to take a point in Rn, and we're going to map it to another ordered n-tuple in Rn. And I'm going to put a little tilde here because it's not quite the same, but it's a little bit like this one was. We were really mapping from a real number to a vector, but then we focused on the terminal point. Here, we're really mapping from a real number to a vector. And every time we sketch it, we sketch a real, or an ordered n-tuple in n-dimensional space. That's a location. And then we are mapping it to a vector. So it's not really Rn to Rn, but we can think of this like Rn to Rn. So I think it's a natural extension of everything we've done so far. It's the 3D version or the ND version of this. We won't talk about it in this class, but I guess we could also go from Rn into Rm, where Rn and M are different numbers. Okay, so that's what we're going to get to in a little bit. Now, one other thing that this chapter is about, it's about extending this idea of multiple integration. In Calculus 1, we were integrating over a subset of the real line. So we're integrating over something that looks like this. And then in this class, we said, rather than integrating over a subset of the real line, let's integrate over a region in flat two-dimensional space, or let's integrate over a solid region in three-dimensional space. What we're going to do in this chapter is much more general. We're going to be able to integrate over pretty much anything, as long as it has the right qualities, and we'll talk about what those little qualifiers are. But we're going to talk about integrating over lines and what are called line integrals. So rather than integrating over some subset of the real line from A to B, we're going to integrate over a curve. So we'll have some curve, and I'll just make it in three-dimensional space, for example. Same curves that we talked about. In our chapter on vector valued functions or vector functions. So maybe this is a curve C, and it's given by R of t, and t starts at A and t ends at B. So we start at this location, we end at this location. Rather than integrating over some subset of the real line, we can integrate over this. We'll talk about that very shortly. And then after we talk about line integrals, we're going to discuss surface integrals. And that's integration over a surface. So what if we said, I don't want to integrate over the XY plane, and I don't want to integrate over a solid region Q. Instead, I want to integrate over this. Let me integrate my function over this surface S given by z equals f of x, y. So we're not limited by the real line anymore. We can integrate over anything. And we're going to show you how to do that in this chapter. And there's some really interesting theorems that go along with integration over curves and integration over surfaces. So that's the overview. That's where we're going. And there are some really beautiful applications in physics for both of these guys. Okay, so let's get back to vector fields. Now, in general, a vector field, which I'm going to abbreviate as VF, a vector field F assigns an n-dimensional vector to every point in its domain and its domain is a subset of n-dimensional space. So F maps from Rn into Rn. If n equals 2, our vector field F would map from 2D into 2D, or something that's kind of like 2D. I'm going to use that little tilde sign because it's really not just a point, it's a vector. And if n equals 3, our field would map from 3-dimensional space to 3-dimensional vectors. I guess I'll call that 2D vectors, and this I'll call 3D vectors. And of course, this is ND vectors. The notation that we'll use is this. Different textbook authors use different letters, but these are the letters I'm going to use in our class. For fields in the plane, we'll say f of xy is m of xy times I hat plus n of xy times j hat. Or we can use this component form, which I think is more convenient. It's a little bit shorter. So this is going to assign a 2D vector to every point xy in the domain of this guy. And f will be continuous if the component functions m and n are continuous. And of course, if we're in 3D, we assign to every point in the domain of this field, which is some subset of 3-dimensional space, a vector that has 3 components. So here we go from R2 into R2, or from R3 into R3. And I will write out what I stated about continuity. F is continuous if and only if its component functions are continuous. So here's an example. Let's say we've got f of xy equals negative y times I hat plus x times j hat. This is a vector field. At 0, 0, There's not much going on there. It's just the 0 vector. When x equals 1 and y equals 1, x is 1, so the y component of this is 1. If y equals 1, the x component of the vector is -1. So if I wanted to graph it, this is what I would do. I go to this point, x equals 1, y equals 1. I would start there. That would be my initial point. And then I would draw a vector that goes -1 unit in the x direction and 1 unit in the y direction. So I'd go back 1 and up 1. And that's what that would look like. Okay, let's see what happens at x equals 0, y equals 1. If x is 0 and y is 1, we get this. I'm replacing x with 0, I'm replacing y with 1. So it's -1 times I hat. So I start at this location. I go to x equals 0, y equals 1, that's right here. And I draw a vector. I draw the vector -1 times I hat with this as its initial point. So I'm just going to go backward 1 unit in the x direction. You could do this for different points. I'm just going to do a few more. I think I'm just going to go sort of around this little 2 by 2 square that's centered at the origin. So let's go to -1, -1, and -1, 0, and oops, I guess I wanted -1, +1. Can do that separately. -1, +1, 0, -1, and +1, 0. Now I picked a very simple field, but I want you to see the pattern. It's not just this x and this y are the components of the vector. That's not how it works at all. These are formulas for the components of this vector. So, and the y component always turns out to be the x value at that location. So when our x value is -1, that means the y component is going to be -1. When the x value is 0, the y component will be 0. When the x value is 1, the y component will be 1. Now the x component of this field is given by the opposite of y. So I look at the y value and I multiply it by -1. And there's the y value there is 0. So now let's sketch all of these vectors. When x is -1, y is -1. That's our location where we're starting. At that point, the vector goes 1 unit in the x direction and -1 unit in the y direction. Okay, so we've graphed, this one was just boring. There's not much going on, so got that. We graphed that one and that one, graphed that one. Now I want to go to x equals -1, y equals 0, so we're here. And it looks like we go 0 units in the x direction, -1 unit in the y direction at that point. Okay, at x equals -1, y equals 1, that's this location. The vector goes -1 unit in the x direction and -1 unit in the y direction. So we go back 1 and down 1. Okay. At x equals 0, y equals -1. So we're right here. And we go 1 unit in the x direction and 0 units in the y direction. And at x equals 1, y equals 0, so we're here. We go 0 units in the x direction and 1 unit in the y direction. You can see that this is very tedious, takes a long time. Most of the time if I want to graph a vector field, I'm gonna let a computer do it for me. But each point in the xy plane is associated with a vector. Now if I were able to draw all of the vectors, all you would see is red. there would be no vectors there. So we can't actually draw a vector field. We can only draw a few representative vectors in a vector field. But the idea is the same. This is just taking, it's just taking every xy here in the domain, and the implied domain is all real numbers because y can be anything and x can be anything, and this, the components will be well defined. So all real numbers for x and all real numbers for y, so it's all of two-dimensional space is our domain. And then every point in two-dimensional space is assigned a vector. Okay, so that's the idea, and we'll look at some more examples of vectors in just a second. But just in general, a vector field in R2 is going to look something like this. At every point xy, you go to that point and you plot a vector. And the vector is given by m of xy times I hat plus n of xy times j hat. So you plot that vector, and then you go over here and you plot that vector, and you go here and you plot that vector, and there, and you plot that vector, and so on. It's so tedious that we typically have a computer do this for us. But that's the principle. That field F assigns a two-dimensional vector to every point in two-dimensional space. Now this one is very similar. It's even harder to draw. But this assigns a vector to every point in its domain, which is a subset of three-dimensional space. I think I may have misspoke here. This only assigns points, vectors to points in its domain, which is a subset of two-dimensional space. So basically, we're just going to have a bunch of vectors over here as well. Here's a point, and there's a vector. Here's a point, and there's a vector. Maybe they look like this. And that should not be curving. It should be just a straight line, because vectors don't curve. Not by themselves, not individual vectors. A field of vectors might seem to have some motion. And maybe it does if this field was a function of time, but this field is just a function of position, x, y, and z. Okay, so you get a bunch of vectors, and they're all over three-dimensional space, and you'd probably see some overlap. And it's sort of a mess to look at, but you get the idea. Every point in the domain, which is a subset of three-dimensional space, is associated with a three-dimensional vector. You guys have seen some vector fields before. I'd just like to list some examples for you, and then we'll look at some better pictures than this and better pictures than my cartoons from another textbook. So here are some examples of vector fields that you're probably already familiar with. Gravitational field. Is a vector field. An electric field is a vector field. Magnetic fields are vector fields. These gravitational and electric fields, electrostatic fields, we can think of those as force fields. It sounds like science fiction, but it's a real thing. It's just saying, okay, there's a certain force associated with every location. Velocity fields for fluids. If you've got a fluid and it's moving, call that flow. Every point in the fluid has a certain velocity. The field associated with that velocity is called a velocity field. And one example that you've already seen in this class, even though you didn't realize it, or you may not have realized it at the time, was the gradient of F. When we looked at a surface given by z equals f of x, y, and we found its gradient, we said it was equal to this. Well, what does that do? It takes every x, y in the domain of that function well, in the domain of that function where these derivatives are well-defined, partial derivatives are well-defined, and it associates them with a vector. And remember what that vector tells us. It tells us the direction of greatest or steepest ascent, or the direction of greatest increase of the function. And if I want the magnitude of that, or if I take the magnitude of that, I can get the slope in that direction, or the magnitude of the greatest increase at that particular point in the function, the greatest increase in the function at that point. So let me show you some pretty pictures, just because this one little vector field with, let's see, how many vectors did we draw? We drew 7. It really doesn't do vector fields justice, and then this just looks like a mess, but I think it helps a little bit. It helps you understand the idea. Now, the pictures I'm about to show you are from this textbook. I used this when I was at Oklahoma State. It's Vector Calculus, 5th edition by Marsden and Tromba. Let me show you some pretty pictures. Okay, so here's some field vectors in 3-dimensional space. It's very similar to the pictures that I was drawing for you. And you can think of the velocity field describing velocity of fluid flow in a pipe, like this. That velocity field might be a function of x, y, z, and t, or maybe not. Maybe the whole time, every particle at that location has a certain velocity. So you might have a velocity field that depends on position only. This is called a rotary vector field. And it's actually the same field that I was sketching for you. Negative y times I hat plus x times j hat. Here's my picture. I only had 7 vectors, but if I was able to draw more vectors quickly, I could draw something like this. See how many calculations we would have to do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times 6 rows. We'd have to do 66 little calculations and then sketch 66 little vectors. No thanks. I think we get the idea, or I hope we get the idea. But this is what that field looks like. If you have a tub, you might have a field describing the velocity of that fluid in that tub. We've got a vector field that might represent the gradient of a temperature function. So maybe our temperature function is T of X, Y, and Z. Well, temperature is going to flow from hotter places to colder places. The heat flux vector, that's going to be given by the gradient of T, goes this way. Actually, I think I may have said that the other way around. They have the negative gradient of capital T here. The temperature gradient is going to go the opposite way, because the gradient is going to point to where the temperature is increasing the fastest. So you'd have to have the negative gradient to see where it's decreasing. It's going to flow toward the colder regions. That's right. Negative gradient makes sense here. Classic electric or a gravitational force field, just due to mass. So we've got another gravitational field. We've got some massive object there. Everything's attracted to it. We've got some other pretty fields over here. All these vectors are sort of pointing out from the origin. All these vectors are pointing in. Okay, that's the idea. So those are some vector fields for you. But again, main idea is if I've got a vector in the plane, it's going to look like this. Every x, y, for which this is well defined, is going to correspond to a vector over here. And every x, y, z, for which this is well defined, will correspond to a 3-dimensional vector here. So gravitational fields, electric fields, magnetic fields, force fields, velocity fields, and the gradient are some examples of that, some examples of fields. Now I'd like to tell you about the del operator. You've seen it before, but this del operator is going to allow us to operate on vector fields. It also operates on scalar fields. It looks like a vector, but it's really not. So we can think of it as a vector with components, partial of f, or partial with respect to x, partial with respect to y, and partial with respect to z. But it's not a vector. It's an operator that behaves like a vector. Or maybe we'll say it's an operator with vector characteristics. This is an operator in the same way that ddx is an operator. So this by itself means nothing, but if I put something in front of it, let's say x squared, that doesn't mean ddx times x squared. That means take the derivative with respect to x of x squared. This operates on this and it gives us a new function, 2x. So we apply this operator to something. It's acting on something. So we're thinking of it as operating on that something. This is very similar. The del operator, it's just got this vector quality to it. So we've already seen the gradient. Del f. And let's say that f has two variables. So f is a function of x and y. Well, in that case, our del operator would only have two components. Now, one thing I will show you, it's sort of standard notation when it comes to the del operator. I don't know why I said sort of. It is standard notation when it comes to the del operator. I'm thinking of it as this times I hat plus this times j hat plus this times k hat, but I can't put the I hat in front of that because then it looks like I'm taking the partial derivative of I hat with respect to x, which really doesn't, well, it could make sense, but we don't want to do that. That's not what we mean when we say this. The del operator is sometimes written this way. It's I hat times the partial with respect to x plus j hat times the partial with respect to y plus k hat times the partial with respect to z. And again, the only reason we don't put the I hat, j hat, and k hat on the other side is because we want to make it clear that we're not differentiating those standard unit vectors with respect to x, y, and z. We're just saying operate on something and then multiply it by I hat. Then operate on something this way, take the partial with respect to y and multiply it by j hat, and then take the partial with respect to z and multiply it by k hat. So when you see the del operator operating on a scalar function f, you might think of it this way. If f is 2D, we'll use the del operator, which is also 2D. And now this almost looks like scalar multiplication. It looks like I'm taking a vector, I'm multiplying it by a scalar. The way I multiply a vector by a scalar is I just distribute, right? I say this component times the scalar plus this component times the scalar. It's kind of like that, but every time we would typically multiply, we're going to operate on the function or act on the function. So we're going to say, just for your notes, rather than multiplying, the operator acts upon the function. And this, oh, excuse me, it's off the screen. But we're doing this in exactly the same way that we did it over here. We said, operate on x squared. Take the derivative with respect to x of x squared. That's going to give me 2x. So what this is I'm going to treat it like vector multiplication, like taking a vector and multiplying it by a scalar. But everywhere that I see would typically have multiplication, I'm going to take the partial of F with respect to whatever is there, whatever operator is there. So this becomes the partial of F with respect to X and the partial of F with respect to Y, which, as you know, is the gradient function, pointing in the direction of steepest ascent or greatest increase of the function. And then if you want the slope or the instantaneous rate of change of the function at that location, you just take the magnitude. Okay, so that is one operation with the del operator. Now another operation looks like a dot product So this is called the divergence of a vector field F. And sometimes, or it's often written this way. Sometimes you'll see it written that way. Divergence of F is the del operator. It looks like dotted with F. So let's say F is a field in 3 dimensions. So F has 3 components: M of X, Y, and Z, N of X, Y, and Z, and P of X, Y, and Z. So at every location in its domain, we're going to have a different X component, Y component, and Z component. Now, if I take the dot product of this, normally I would just multiply and add, multiply and add, and multiply and add. This time, instead of multiplying, I'm going to operate and add. So I'm going to take the partial with respect to X of M, and then we add the partial with respect to Y of N, and then we add the partial with respect to Z of P. And that gives us divergence. Now, intuitively, we can interpret this way. Divergence is a measure, and this is just the intuitive definition. I'll give you a proper definition, a little bit more precise definition, when we talk about the divergence theorem. But this is a measure of how much the field spreads out at a point or diverges from a point. So let's say I've got a point that looks like this. And let's say I've got a field that looks like this. And let's say I've got a field that looks like this. So here we've got 3 fields. They're in the plane. And the question is the divergence of each of these fields positive, negative, or 0, or is it impossible to tell? Well, one way that we could figure it out is we could try to write an equation for each of these fields. So we could write F as M of X, Y, and Z, N of X, Y, and Z, and P of X, Y, and Z. Or we could just remember this intuitive definition. This is a measure of how much F spreads out or diverges from a point. I think everyone can see that here, that field is spreading out more and more and more the farther we get from that point. So the divergence here is positive. Because it's spreading out. Here, divergence is 0. And that's because if I look at the x component of each of these vectors, well, there's no x component to any of these vectors. The x components are staying exactly the same. Well, they're all 0. So the partial of m with respect to x is 0. What about the partial of n with respect to y? What about the y components? Are they staying the same? I was trying to draw a graph where they were staying the same. The y component is supposed to be the same for all of those vectors. So as y changes, the y component, or you're saying, okay, well, what's the change in the y component with respect to y? So I'm here at this location, and then I let y increase by a little bit. Did the y component change? No, not at all, because they're basically all the same vector. So that's 0, and there's no z component. So this one has a positive divergence, because you can imagine that it's like spreading out. And over here, we've got a 0 divergence. And over here, I believe we have a negative divergence. And let's think about why that is true. Again, there's no x component, so that partial is 0. And let's look at what happens to the y components. Well, the y values, or the y component of the vector, is a negative y value. And then as y increases, what's going on there? As y increases, is that negative value getting more positive or less positive? Or excuse me, more negative or less negative? I think it's getting less negative. So actually, I think that's wrong. This divergence is positive here as well. Okay. So the y component is increasing as you go in the y direction. So I'll have 0 plus this, which is increasing, and then we've got 0. So these ends are increasing with respect to y. So the divergence would be positive. So we've got positive divergence, 0 divergence, and positive divergence. But intuitively, it's just a measure of how much the function spreads out or diverges from a point. I read in a physics book this analogy. I thought it was a great analogy. It said, imagine sawdust on water. So you've got some water. And you throw some sawdust in there. So you just like sprinkle a little dust on it. Using the velocity field of that water as our field F, if the sawdust starts to spread out, so initially it's here, but then in a few minutes it sort of goes farther away, it's getting farther and farther away from where it started. That means the divergence at that point is positive. Now, if we threw some sawdust on the water and then it all started to collect together, then the divergence would be considered negative. Now you can see that on this one, divergence is positive because we're expanding from this point. If I turned all of these vectors around and multiplied them by -1, all the vectors would be going towards that point. So in that case, divergence would be negative instead of positive. So here, everything is going away, it's spreading out, so divergence is positive. If the vectors were pointing the other way, that sawdust in our fluid would be collecting together, so divergence would be negative. The point where this happens, that point where the sawdust is spreading out or collecting together, we say that that point is a source if the divergence is positive, and we say that that point is a sink if the divergence is negative. Just think of like the source being like your faucet and the sink being like your drain. Do we have water going like sort of coming out from that location, sort of expanding the fluid, or do we have water going in at that location and the fluid sort of disappearing at that point? That analogy always sort of bothered me. I was like, but where is it going? We're not worried about that. We're focused on the field itself. And if it's not spreading out or collecting together like this, then the divergence is 0. Okay, the last operation on a vector field is called the curl. Sometimes you'll see me write it like that. That's just for emphasis to remind myself that the curl yields a vector. But we can think of it this way. It's like taking the cross product of the del operator with the field F. Now that field F has to have 3 components in order for us to take a cross product. If our field was 2D, we could always just imagine it was in 3D with a 0 for the Z component. So in the second row of this determinant form of this cross product, we've got those operators, partial with respect to X, Y, and Z. And then down here, we've got the components of F, which are M, N, and P. You just evaluate this, cross out this row in this column. You get partial of P with respect to Y minus partial of N with respect to Z times I hat plus, cross out this row in this column. Don't forget to multiply by -1. Partial of P with respect to X times J hat minus partial of M with respect to Z times K hat, or times J hat, excuse me, plus, cross out this row in this column, partial of N with respect to X minus the partial of M with respect to Y. Now, I don't actually ever memorize this formula. Some people have this memorized. I don't memorize it. I just write down that determinant form every time. Now, this curl has this interpretation. This is just the intuitive interpretation. Curl at a point. If our F represents like some fluid, like air or water, or something like that, this is a measure of how much the fluid swirls around that point. So it's actually, if we're talking about fluid swirling around a point like this, so maybe that's our field. Let's say that that center point is at the origin. I think that we can all see that that's sort of swirling around. It's swirling around the origin. So the curl would be positive. And you say, positive? I thought it was a vector. You're absolutely right. Now the vector is going to be perpendicular to that point where it's swirling. So we've got a vector that's sort of pointing up. Like if this is X, or this is the X-axis and this is the Y-axis, and then because of the right-hand rule, the Z-axis is pointing in the direction of my thumb, so it's going straight up like this. The curl is going to point in the direction of the Z-axis, and if there is some angular velocity right here, the magnitude of the curl is twice that velocity. Or actually, let's just say angular speed. It's going to be twice the angular speed. because if it was velocity, yeah, the orientation, direction would matter, but you get the idea. So it's a measure of how much that fluid is turning around that point. And it's just proportional to that angular speed. The curl is double the angular speed. So here's one with non-zero curl. Here is another vector field with non-zero curl. See how once I get farther away from this line, I'm going farther this way, the magnitude of the field is increasing. The vectors are getting longer. Okay. But if you've got some of the field lines going in one direction and some of the field lines that are adjacent to it going in the other direction, that's going to lead to some curl. That's going to lead to non-zero curl. And it's because of that line right there, where that field switches direction. So in both of these cases, if this is the field F and this is the field, I don't know, F2, F1 and F2, the curl of both of these is non-zero. Because it's a measure of how much fluid is swirling around a point, and there's a fluid swirling here. And if we're at a point on this line, that fluid's going to have a tendency to swirl that way. And even the fluid over here is going to be a little bit influenced by that fluid over there. Okay, now just like we had that sawdust analogy for the divergence, we've got another analogy from physics that helps us to understand curl. So let's imagine you've got a paddle wheel. So that's just like a little round piece of cork, and you put a bunch of toothpicks in it. So there's our cork with the toothpicks in it. And then you set it in some water. Looks like this, like a childlike version of the sun. Not what it is though. It's a cork with toothpicks in it. It's a paddle wheel. If that little paddle wheel starts to rotate about its center, so it starts rotating like this, or it starts rotating the other way, either one would be fine, then the curl is non-zero. So it's not zero at that location where the paddle wheel is. A whirlpool or a tornado, we're in Oklahoma. Or I'm from Florida, hurricanes. That's a curl where the magnitude of the curl is very large. So again, it's a tendency to rotate. And in general, it's if F represents a fluid, or it's not a fluid, but the velocity field of some fluid, then the curl of F yields another vector field called vorticity. And it's given by this. And the magnitude of the vorticity is 2 times the angular speed. And the direction of the vorticity is just pointing directly up from that point where it's rotating. So if it's rotating this way, it's going to go this way. Or I guess you could say it's either going to go this way or this way, but it's the curvature, or not curvature, the fluid is swirling counterclockwise relative to the direction of this guy. Okay. Let's calculate some divergence and some curl. Actually, but right before we do that, let's look at those other pictures that we talked about before. Now remember, the intuitive definition of curl is a measure of how much the fluid is rotating or swirling around the point. What do you think? Is the curl positive, or is the curl 0 or non-zero here? Is the fluid's rotating around any point? No, it's just sort of going out. So here the curl is the 0 vector. What about this? Is there any swirling? No. What about this guy? Similarly, no. Okay, and now let's think about divergence. Is the fluid tending to move away from this location? I don't think so. I think that's a divergence of 0. And what about here? What about divergence here? That one's a little bit harder. For that one, I might want to do some calculations and see what the divergence would be. Okay, so let's do a couple of examples where we actually calculate the curl and the divergence, and then I'll tell you one more fact about curl and divergence. Okay, so we're going to find the curl and divergence of some fields. So here's a field. Let's say our field is natural log of x squared plus y squared times I hat, xy times j hat, and natural log of y squared plus z squared times k hat. And we're asked to find the divergence of this field. So the divergence of F can be thought of this way. It's taking the del operator and dotting it with F. So basically, you're just going to take the x component of this and take its partial with respect to x. And take the y component of that and take its partial with respect to y. And the z component, you're going to take its partial with respect to z. And you're going to add all of those together. My x component was natural log of x squared plus y squared. My y component was that, and my z component is this. So now I'm going to take the partial with respect to x of this guy. And we're just adding these. Divergence yields a scalar function of x, y, and z. So I've got natural log of a function. So I'll have to use the chain rule. So I'll have 1 over the function by the chain rule. Derivative of the natural log of a function is 1 over the function, times the derivative of the inside with respect to x, treating y as a constant. So we just get 2x there. Now we're taking the partial with respect to y of this. Well, x is being treated as a constant. So this is a constant times y. The derivative of a constant times y is just my constant. And with the last component, we're taking the partial with respect to z of this function of y and z. So we have to use the chain rule. Oops, that's my inside function. So I have 1 over the function times the derivative of the inside with respect to z. The derivative of y squared with respect to z, if it's a partial derivative, so we're treating y like a constant, is 0. And then we'll multiply by the derivative of z squared, which is 2z. So we get this. We get 2x over x squared plus y squared plus x plus 2z over y squared plus z squared. Now this is the divergence as a function of x, y, and z. At particular x, y, and z values, we're gonna get numbers. We're gonna find out is that particular location a source or a sink, or is it neither? So you might try, let's try x equals 1, y equals 0, and z equals 1. So the divergence of F evaluated at 0, or let's say 1, 0, 1. So I replace x with 1. I replace y with 0. And I replace z with 1. So we're going to get 2 plus 1 plus 2, so that's 5. Since 5 is greater than 0, we would say that if this represented some fluid, that fluid is expanding there at that location. It's diverging from that location. Or in general, like we're thinking of it as spreading out. So anything that would follow along with that field would be sort of dissipating. It would be spreading out, like the sawdust in the water example. Okay, so that's divergence. Easy breezy. You just take the components, you take the partials of each part respectively with respect to the appropriate variable, and then you add them together. And then let's compute the curl. So I'm using that determinant form. Put partials with respect to x, y, and z here. It's our del operator. And then we'll put the components of f down here. I want to use a different field this time. Let's use this. This is a simple looking field. Got x squared times z minus 2xz. This is x squared z times I hat minus 2xz times j hat plus yz times k hat. Okay. So I cross out this row in this column, and then I take the partial with respect to y of yz. And then I subtract the partial of negative 2xz with respect to z. Okay, then we cross out the row and column containing j hat. Don't forget the minus. Then we do the partial with respect to x of yz. Oops. And we subtract the partial with respect to z. It's that diagonal of x squared times z. You don't have to write out all of these steps if you don't want to. I think it's helpful when you're just starting to learn. Now we're cross out the row and column containing k hat. You take the partial with respect to x of this guy. And then you subtract the partial with respect to y of that guy. All right, easy breezy. Now I just need to do my partial derivatives. I'm treating y as my variable, as z as a constant. So this is the derivative of a constant times y. The derivative of the constant times y is just the constant. Over here, I've got a constant times z, because I'm treating the x as a constant. The derivative of a constant times z is just that constant. We've got a negative that we bring down. Partial with respect to x of this, well, there's no x's in it, so that's just going to be 0. Because it's all constant with respect to x, the derivative of a constant is 0. Then we're subtracting the partial of this with respect to z. So it's a constant times z, so we bring our constant down. Over here, taking the partial with respect to x, I've got a constant times x. The derivative of a constant times x is just the constant. And now over here, there are no y's in this, so this is constant. The derivative of a constant with respect to y is 0. So we get z plus 2x, a negative x squared, that's x squared, and a negative 2z as our z component of the curl. Now, if somebody asked you to compute the curl at a particular point, let's say they wanted the curl at x equals 2, y equals negative 1, z equals 3, you would just replace all the z's with 3, place all the x's with 2. There's no y in our definition of the curl this time. And then you just simplify. So we've got 4 plus 3 is 7, and then a 4, and then a negative 6. So that curl is non-zero. So that means there is some rotation in that at that point. If this field represents the velocity of some fluid, that field has some rotation at this location. And that's the vector that's representing that rotation. Okay. A couple of other things I just wanted to share with you. If the divergence of F is 0 all the time, for all x, y, z, let's just say for all points in its domain, because we could be in 2 dimensions or 3 dimensions, then we say that F is divergence free. That means there are no sources or sinks anywhere. Now, if the curl of F is the 0 vector for all points in its domain, we say that F is irrotational. So there's none of that sort of swirling motion at any point within the fluid if F represents the velocity of a fluid. I just want to mention one last fact to you. If we have a field F and it has components m, n, and p, and m, n, and p have continuous second partial derivatives, then it turns out that the divergence of the curl of F is going to be 0 every time. Now we can verify this, but I think I'll let you do that if you want to. All you would do is find the curl of F in general. So you find this formula, and then take the derivative of this guy with respect to x, add the derivative of this guy with respect to y, and add the derivative of this guy with respect to z. You're going to see a bunch of mixed partials that cancel out because they might be written in a slightly different order. You might have the partial of p with respect to x and then y, and the partial of p with respect to y and then z. but we know that those are equal to each other if the partials are continuous. So they'll just disappear because you'll have the same thing basically with opposite signs. I'll let you prove that for yourself if you want to. Let me think I'm trying to think if there's anything else I need to tell you about curl and divergence. I can't think of it right now. I remembered something briefly about curl and divergence that I wanted to tell you, and then it sort of fell out of my brain or something. Sorry about that, but let's review what we went over. So we started this video by talking about multivariable calculus and how we used to map from R into R. In Calc 3, we mapped from R into Rn, and then Rn into R. And then finally, in this chapter, we started mapping from Rn into Rn with vector fields. And then we said, you know, what we're about to do is we're about to integrate over curves and surfaces. So we don't have to integrate over intervals anymore, and we don't have to integrate over either regions in the XY plane or regions in solid space. We can integrate over any kind of surface like this. Well, not every kind of surface, but most surfaces that satisfy certain conditions. We're going to be able to do that. And then we discuss what a vector field is. We said vector fields are represented by vector F, usually a capital F. It assigns an n-dimensional vector to every point in its domain, and its domain is a subset of n-dimensional space. So we're going to look at vector fields in the plane and vector fields in space, but everything that we've done applies to n dimensions as well. But here's some ways to visualize it. Every xy in the plane is associated with a vector, or every xyz in space is associated with a vector, or some subset of the plane or some subset of space if those vector fields have different, slightly smaller domains. And we said that those are continuous. Vector fields are continuous if the component functions are continuous. And then we looked at an example and we tried to graph it, and we saw how tedious it was. And then we looked at a bunch of examples in the Marsden vector calculus book. But you're familiar with vector fields: gravitational fields, electric fields, magnetic fields. We can call these force fields, which makes it sound like sci-fi. Velocity fields of fluids like air and water, and gradients are all vector fields. And then we said, okay, now that we know that, that's pretty cool. Let's talk about some operations on vector fields. In order to have operations on vector fields, we introduced the del operator. It's like this derivative operator from Calculus 1, but now it has multiple components. It acts like a vector. Its first component is this partial with respect to x operator. Its second component is its partial with respect to y operator. And the third one is a partial with respect to z. And this is the del operator in 3 dimensions, but it could just as easily be done in 2, and it could just as easily be done in n dimensions. It would just have n components. But the idea is it acts like a vector, but every time that vector would multiply something else, instead of multiplying, it's going to operate on it. Just like this is not multiplication, this is an operation. I'm saying, okay, let's take the derivative of x squared with respect to x. It's telling me to do something, and then we do it. That's the same thing here. When I take my del operator and I operate on this scalar function f, I get the gradient. So I take the partial with respect to f, of f with respect to x, and I multiply it by I hat. And then I add the partial of f with respect to y, and I multiply it by j hat. Okay, so now we've got this del operator, and we can do all kinds of things with it, things that we would typically do with vectors. So we can take the divergence of a field by taking that del operator and almost dotting it with this field. That's the notation that we typically use. Even though this isn't a vector, it helps us remember what the divergence is. It's like I've got this vector operator operating on this vector in the same way that a dot product would, but instead of saying this times this, I'm going to say the partial of this with respect to x. Instead of the partial with respect to y times n, it's the partial of n with respect to y, and so on. So divergence is really simple. Just take the components, differentiate with respect to the appropriate variable, and add. And we said divergence is a measure of how much the field spreads out, or diverges from a point. So here divergence is positive. Here there's no spreading. And here divergence is positive, even though initially I thought it was negative, because as y increases, the y component, which is represented by n, becomes a little less negative. So n is actually increasing as y is increasing, so the divergence is positive. There's no x component, so it's that part is 0. So we've got 0 plus a positive number plus 0 is a positive here. Now curl is a measure of a tendency to rotate about a point. There's no tendency to rotate here or here or here. But there does seem to be tendency to rotate there or there. We said there are 2 ways you can think about divergence and curl intuitively. You can think about sawdust on water, just putting some dust in some water and then seeing if that dust spreads out over time or collects together over time, because that dust is going to follow the velocity of the fluid. If that dust spreads out, the divergence is positive. If the dust collects together, the divergence is negative. To intuitively understand the curl, we talked about putting this cork with a bunch of toothpicks in it called a paddle wheel in some water or in some fluid. If that paddle wheel starts to turn about its own axis, so it just starts to rotate this way, then the curl is non-zero. And then we did a couple of calculations and a couple of definitions. If curl of F is always 0, we call the field irrotational. If the divergence of F is always 0, we say that the field is divergence free. And we said if the components of F have continuous second partials, it turns out you can take the divergence of the curl and you'll always get 0. So that's it. That's our summary. And I'll see you in the next video.